Good afternoon, Internet. I am Matt Buyak, and in this video we'll be taking a look at the 39th problem from the Project Euler problem archive. Now, this problem asks us to consider right triangles with integer side lengths and perimeter given by p. And in particular, it asks us to find the value of p less than or equal to 1,000, such that the number of triangles with that perimeter is maximized. Now, you might recall that if A, B, and C are integer sides of a right triangle, that we say A, B, and C form a Pythagorean triple. And I did a whole video on Pythagorean triples a little while back, and we derived a procedure for generating Pythagorean triples. So we'll definitely be using the procedure from that video in this solution. As usual, we will copy our template directory to make our problem directory and open up our analysis file. And we'll also open up the notes from that previous video and go down to the key result down here. And we'll copy that over. We don't need this stuff about u and v. That's just has to do with our derivation. By the way, if you want all the details on how we came up with this procedure, I'd recommend that other video I mentioned. I'll put the link to that in the description. Okay, so our procedure here says that if we have odd integers n and m, with n and m relatively prime and m less than n, and then we have a, b, and c given by these equations here, then a, b, and c will form a primitive Pythagorean triple. So let's start with a couple of key definitions just in case you've forgotten. Let's see, we say that n and m are relatively prime if the greatest common divisor of n and m is equal to 1. That is, if there is no integer larger than 1 that divides both n and m evenly. Also, we say that a Pythagorean triple A, B, C is primitive if A, B, and C are relatively prime. Okay, now obviously we don't want just the primitive Pythagorean triples. We want all of the Pythagorean triples. And so our original procedure here will not be quite adequate. Fortunately, we can get all the Pythagorean triples from the primitive Pythagorean triples just by scaling them by the natural numbers. Now, there's another key property of this procedure that is worth mentioning, and that is it generates the Pythagorean triples uniquely. That is, we don't have to worry about creating the same solution multiple different ways. And that's going to have big implications for our implementation once we start writing some code, because we won't have to double check to make sure we're not counting the same solution twice. We just need to keep track of the number of solutions that we have found for a given value of p. Okay, so let's get into looking at how we determine the perimeter that corresponds to a particular Pythagorean triple. Obviously, the perimeter is just going to be a plus b plus c. And we can get that just by substituting in these values from up here. Okay, we have a plus b plus c. And that is going to simplify to just n times n plus m. Okay, Now, before we can actually look at implementing our solution, we're going to have to come up with some reasonable upper bounds for m and n. You might imagine that we're going to have nested for loops with m being the outer loop and n being the inner loop, and n ranging from m plus 2 up to the largest value of m that doesn't cause this expression here to be greater than 1,000. But we still need to come up with an upper bound for m. And in order to do that, we should consider what is the smallest perimeter that we can have for a given value of m. And I think it's easy to see that that occurs when n is exactly m plus 2. So we'll say the smallest perimeter for a given value of m occurs when n equals m plus 2. That is, the perimeter will be, and then we can just substitute in m plus 2 for n. That's going to be m plus 2 times m plus 2 plus m. And that's going to work out to 2m squared plus 6m plus 4. And we can set that to be less than or equal to 1,000. And simplify slightly, and we get this expression here. Okay, so if we wanted to, we could pull out the old standby, which is the quadratic formula to find the solution for this equation. But often I find it to be simpler just to do a little bit of guess and check. So if we pull up our calculator here, we see that our value for m is going to be roughly the square root of 500. That's going to be roughly 10 times the square root of 5, or a little bit bigger than 20. And so that's going to be maybe 21 squared plus 3 times 21. Just a little bit too big. So let's try 19 squared plus 3 times 19. Less than 498, we're good to go. So we have our upper bound for m is m less than or equal to 19. Okay, good to go. Now, before we can actually write code, there's a particular algorithm that we're going to need in our toolbox. And just switching back over to our browser real quick here, we can see that they actually did add the algorithm in question, greatest common divisor, into the STL in C++17. But you might be using an older version of C++. And honestly, this function here, greatest common divisor, corresponds to possibly one of the greatest algorithms of all time, and that's Euclid's algorithm. So I think I'm going to take this as an excuse to take a brief excursion into looking at this classic algorithm. Over 2,000 years old, still relevant today. In terms of utility and elegance, really hard to beat Euclid's algorithm. So let's take a quick look. Okay, so let's see. Given integers n and m, determine greatest common divisor of n and m. And we'll say, suppose n is equal to BD and m is equal to AD, where d is equal to the greatest common divisor of n and m. Okay. Now we'll also suppose that when we divide n by m, we get quotient q and remainder r. That is, n is equal to qm plus r. And it might not seem obvious how any of this is useful, but wait until we do a little bit of rearrangement and some substitutions. We see r is equal to n minus qm, and substituting in our definitions for n and m, we're going to get bd minus aqd. And then we can factor out d to get d times b minus aq. And so in particular, we see that if d divides both n and m, it also divides r. But r is a smaller integer than either n or m. And so we can repeat this procedure, getting smaller and smaller values until we find our value, the greatest common divisor, which divides every integer in the sequence. I think it's probably easiest to understand if we just look at an example. So let's suppose n is equal to 165 and m is equal to 105. Well, then we can write 165 is equal to 1 times 105 plus 60. That's writing 165 as the m times its quotient plus the remainder. And we can repeat that procedure then, saying 105 is equal to 1 times 60 plus 45. And 60 is equal to 1 times 45 plus 15. And 45 is equal to 3 times 15 plus 0. And the algorithm terminates when you end up with a remainder of 0. I think it's easy to see that 15 divides itself. It obviously divides 45 evenly, and so because the remainder is 0. And so we can construct an inductive argument that 15 must divide every integer in the sequence here, all the way up to 105 and 165. I'm being a little bit informal with the proof here. If you like more information and a more formal explanation of Euclid's algorithm, there's lots of resources online. For example, the Wikipedia page that I showed you just a moment ago. Okay, so now I think we're ready to start writing some code. Let's open up our main.cpp. And we'll start by implementing Euclid's algorithm as I just showed. So we'll say greatest common divisor of a and b. And we're going to need the remainder. And we'll say while b is not equal to 0, the remainder is going to be r is equal to the remainder of a divided by b. And then we'll say a is replaced with b is replaced with r, and we just return a when b equals 0. Okay. Now we're also going to need some sort of data structure for keeping track of the number of solutions that we found for a particular value of p. And we could use just a standard C-style array to do this, but these days I kind of like using the C++ style. So this is just going to be an array, excuse me, not 10, 1001, 1001 integers. Note that because arrays are 0-based, if we want to access the if we want to access element 1000, we actually need space for 1001 elements. So that's why this is what it is. and we'll just call that solutions. And we will need to include array. Okay. And then down here, we're going to need n and m, probably p for the perimeter. And recall that we need to scale our primitive Pythagorean triples to get all the Pythagorean triples. And so we're going to need some scaling factor k. All right, so then we'll say for m is equal to 1, m is less than or equal to 19. Remember, we determined that upper bound in our analysis earlier. And then we're going to increment m by 2. Be careful not to increment m by 1 because m has to be only the odd integers. Okay. Then we'll say for n is equal to m plus 2. Again, not plus 1. You don't want any even integers sneaking in here. Then we'll do n times m plus n is less than or equal to 1,000. And n plus equals 2. Okay, so now we'll say if the greatest common divisor of n and m is not equal to 1, that is, if it's greater than 1, then we're going to skip. And then let's say the perimeter is going to be equal to n times m plus n. This is the perimeter that corresponds to the primitive Pythagorean triple. You'll note that as we scale the primitive Pythagorean triple, the perimeter itself will scale by the same factor. So we can say for k is equal to 1, p times k is less than or equal to 1,000, increment k. Okay, and then we just need to record the solution that we found. So we'll say solutions, p times k, and we'll just increment that. All right, so we've generated all of our Pythagorean triples, recorded our solutions. Now we just need to find the best one. And in order to do that, we're going to use a little utility that we wrote a little while back, this Superlatives class here. And again, I'll link in the description to the video where we did the work on this. Basically, just the idea is it's templated. It keeps track of some particular state, and associated with each state, there's a value. And after you've accumulated all of your different states, it will let you know what the minimum and maximum value you've found associated with your states. That's all a bit abstract, so let me show you how we actually use that. Let's see. Let's give ourselves also I, and we'll say for I is equal to 0, I is less than or equal to 1,000 plus I. And we'll need to declare superlatives, and both the state and value are integers. Probably should also actually include that file. Alrighty. And then we can just say super.add_state. And it's going to be, the state is just the value of the perimeter, so that's going to be I. And the score for that state is going to be solutions I. This is just a very common task in these sorts of problems, and so we wrote a little helper class to assist us with that. So now we should just be able to say printf. Let's see, perimeter %d has %d triangles. And that's going to be super dot max state and super dot max val. So that's going to give us the best score that we have found and the perimeter associated with that score. So let's hop back over to our shell and make and solve. And we see that perimeter 840 has 8 solutions. So let's go back over to our browser and take a look at the archive. And we'll see that that does indeed match our solution. So thank you for joining me in this video. I hope you'll join me in the next video where we tackle problem number 40.